Welcome to the next chapter on waves. Many people think of water when the word wave is mentioned. If you look at the motion of a wave, it appears to be traveling in a definite direction. But does it carry anything with it? We can generate waves ourselves by dropping a stone in a pond and see what happens. When the stone hits the water, it sends out ripples in the water. The disturbance spreads in the water surface in a form of concentric circles around the point of origin. The wave can move objects in water or at its edge. To do this, it possesses energy. But where does this energy come from? You see, some of the kinetic energy the rock has as it hits the pond is transferred and carried by the waves. So waves carry energy. And the way we know this is that waves can be very destructive at times. Whether it's sea waves, the light waves of a laser beam cutting through steel, waves in the Earth's crust causing earthquakes, or waves that even bring down giant infrastructure like bridges. And whereas waves carry and transfer energy, do they carry water along with them? If we zoom in to the actual surface, we might pick up some clues to observe. If you look carefully, you will see the water actually moves up and down. It does not travel along with the wave. Waves carry energy without carrying matter. So a ball in the path of the disturbance will be observed to bob on the surface as the ripples move outwards. The ball is, however, not moved along with the wave. The disturbance sets up waves in the water which only transfer energy without dragging the water from one end to the other. By definition, a wave is a disturbance propagated through a medium or space. Waves are electromagnetic or mechanical in nature. Electromagnetic waves do not require material medium for transmission. They include radio waves, radiant heat, light waves, microwaves, amongst others. In this video, electromagnetic waves are not covered, but there is a separate video for that. So we deal with mechanical waves. This kind of waves require material medium for transmission, and this transmission is effected by the vibration of particles in the medium. They include sound and water waves. Mechanical waves can either be transverse or longitudinal. Transverse waves. A slinking spring or a rope may be used to illustrate the formation of this kind of waves. One end is attached to a rigid end while the other is held by the hand and swung up and down at right angles to the slinky or rope. Such waves travel as a series of crests and troughs. So if you think of this slinky, we see that the vibrations are perpendicular to the direction of travel of the wave. These are called transverse waves. Examples of such include waves in water, a string, and light waves. Longitudinal waves. The same slinky spring can be used to illustrate the formation of longitudinal waves. At one end and the other is held in the hand. This end is vibrated in a to and fro moment along its length. And fro vibrations at one end results in the formation of sections of compression alternating with rarefactions along the length of the spring. And if you look at sound waves, vibration is parallel to the rate of travel. These are called longitudinal waves. Note that individual particles in the slinky spring are set in periodic vibrations in line with the direction of the wave motion. The wave motion affects the interparticle spacing. Particles in the sections of compression are pulled closer together, while those in the sections of rarefactions are pulled slightly further apart. Vibrations in interparticle separation are accompanied by variations in pressure, so that sections under compression are at higher pressure while those under rarefaction are at low pressure. This pressure variation causes the wave motion. Progressive waves. These are waves that move continually away from the source. They can either be transverse or longitudinal. Long slinky spring is continuously vibrated at one end. The waves move forward, carrying the energy along its length. Equally, if a stone is dropped onto a water surface, the resulting water waves move, carrying the energy of impact away from the source. As the wave moves away from the source, the energy is spent in an increasingly large area. This causes gradual decrease in its amplitude. A pulse is generated when a single vibration is sent through a medium, and it can be transverse or longitudinal in nature. Wave trains are generated as a result of continuous vibrations at a constant rate in a medium. The medium is distorted into repeated patterns of crests alternating with troughs for a transverse wave, while for longitudinal wave train, the medium is set into repeated patterns of sections of compression alternating with those of rarefaction. One thing to remember is that waves transfer energy from place to place, not any matter. And we can see that here by looking at this lovely duck. As the wave goes through, the duck bobs up and down. Once the wave is gone, it's back to its original position. The wave has carried energy through, but it did not carry the duck along with it. Some key characteristics of waves. First is wavelength, and this is the length of a full cycle of a wave from one point to the next same point. It is easier to think of as the distance between two successive crests or two successive troughs. It is measured in meters and given the symbol lambda, the Greek letter lambda. Amplitude A is like the size of the wave. It's the maximum displacement on either side of the wave from the equilibrium position or the mean position. Frequency is the number of complete waves to pass every second. In hertz, 10 oscillations per point in 2 seconds, the frequency would be 5 hertz. Period T of oscillations is the time taken to complete one oscillation. It is measured in seconds. Usually for any given wave with frequency f, period T is 1 over f, and therefore frequency is equal to 1 over period. Phase and phase difference. Waves can be of the same amplitude but different frequency, or the same frequency but different amplitude. Particles in a wave which happen to be oscillating in the same direction and at the same level of displacement in their oscillation are said to be in phase. If one wave begins at a different time, the waves are said to be out of phase. Next is, and the speed is in 1 second. The meters per second. Now we look at the mathematical relationship between speed, wave, and frequency. Now, the period of a wave is t, then the distance covered t is lambda. Now b is equal to distance over time, that is speed is distance over time, which is given by lambda over t. But remember, t is 1 over f, and therefore substituting that is equal to lambda over f. If we simplify that, we shall have v equals f lambda. Speed is equal to frequency times wavelength. It should be noted that while the rate of vibration of the source determines the frequency of the waves, the speed in a given medium is constant. Now, from the relation v equal to f lambda, an increase in frequency results in a decrease in wavelength. So once a wave is produced, it takes some time to cover a distance. So the wave does carry energy, but only to certain speed, and this speed depends on the kind of wave it is and what it is traveling through. For example, light is a kind of wave that travels very quickly to see the stone falling in water. Sound is also travels much slower than light, and we use the sound to hear the splash as the stone hits the water. Both of these waves travel faster than the water waves, and this is why we see the stone hit the water slightly before we hear the splash, and why we are aware of sight and sound of this before we feel the waves that are produced. Let's take an example. A wave of frequency 4 Hz takes 8 seconds to travel through 24 meters. Calculate its speed, wavelength, and period. Solution. Speed, which is equal to 24 meters over 8 seconds, which gives us 3 meters per second. That is speed. Now wavelength. V is f lambda, and therefore lambda is v over f, which is equal to 3 over 4. That gives us 0.75 meters. That is wavelength. Finally, period is given by one frequency, 1 over f, which is equal to 1 over 4, and that gives us 0.5 seconds. And so, did you learn what a wave is and how waves are produced? Can you tell the difference between transverse waves? And go ahead to give a in each case. Can you explain the terms progressive wave, wavelength, frequency, amplitude? State the equation relating to frequency, wavelength of a wave. Think about that. See you in the next chapter on sound.
Always spot the brightest minds, the ones who think bigger. Push concepts a little further. When you combine theory with practical study, you get university students that are more switched on. That's why Curtin graduates are ready to make a difference from day one to help make tomorrow a better place.